If math has been driving you crazy, or if you're finally admitting you're lazy, and your test grades have been dropping, it's time to get your arrows popping. Hello, ladies and gentlemen. This is Mr. Whitwood for FBT Tutoring, and today we have a wonderful, well-prepared math tutorial for you today. That we do. And this math tutorial is going to be covering the remainder theorem. That's right. It goes hand in hand with synthetic division, hand in hand with solving polynomial functions. And I want to remind you guys to subscribe to FBT Tutoring. That's right. Go ahead and click on that subscribe button there. While you're at it, click on the bell icon that notifies you when we have fresh and new content uploaded to the YouTube channel for FBT Tutoring. Amen, amen. So let's get things underway with the remainder theorem. Here we go. Anytime you have a polynomial, let's say it's f of x, that's function notation, by the way, is divided by x minus c. So if you have a divisor, x minus c here, then the remainder of that is equivalent to f of c. Now, what does that mean to you? The remainder of the division is equivalent to you evaluating the function with the value of c. And what's better than reading this stuff here? Actually seeing it in action. So let's get things going right now. We had a visitor earlier. We had Karina stopping by. She had to leave. And now we have Adrian in the house. And he has his arrows popping, pop, 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 Adrian. That's exactly what you have there. So let's get you up on the screen here, Adrian. And we had Karina there. And these are the people that are here with me live. That's right. So we have 1A, and I want to review what occurs when we normally have function notation and we're asked to evaluate it. Okay, so this is just going to be the regular way to evaluate a function when given a problem such as this. Well, we'll be starting out reading the problem, of course. The directions are important, right? We have evaluate f of 4 given the function f, which equals to 2x to the fourth power minus 5x cubed plus x squared minus 7. Well, what are you going to do with that? We're going to be replacing all the x's with the value 4 and then simplifying this. So we'll end up with 2 times the quantity of 4 raised to the fourth power minus 5 times 4 raised to the third power plus 4 squared minus 7. And then we'll, of course, simplify this. I'll go ahead and attack the exponents first. So we'll have 2 times 4 to the fourth power, guys, is going to be 256. That's right. Minus 5 times 64 is what we have here. Plus 16 minus 7. From here, oh yes, from here, we'll be multiplying 2 times 256. Chosen Creeper is in the house. What's going on? I'm glad you are here with us today, Chosen Creeper. Thank you very much for chiming in. So 2 times 256 is going to give us 512 minus the 5 times 64 is going to give you 320. All right, there you go. Plus 16 minus 7. Let's go ahead and continue to simplify this. Chosen Creeper, make sure that my calculations are correct, please, sir. You know that when I get things started, sometimes I'm a bit rusty here. So I'm going to go ahead and subtract this, guys. Hopefully everything will be in order. We have 192. Plus 16 minus 7. Let's continue here with the addition and subtraction. We'll be adding the 16 here, right? Okay, there we go, there we go. We'll end up with 208 minus 7 to give us a result of 201 as our answer. And this is the way you would normally evaluate a function when given a problem such as this. Well, what we want to compare, of course, we're going to be putting a red box around this. And what we want to compare is the remainder theorem to this process right here. Because what the remainder theorem states is that you can go ahead and use division of the form x minus c with this original function, and the remainder of this will be equivalent to what we just found out. We'll be taking this value of 4 and we'll be using synthetic division. Okay, so we have our synthetic division set up. We'll be placing all of our coefficients from the original function into our synthetic division setup here. And so you'll need to write down all the coefficients in descending order of the variable x. And it looks like this. We'll have 2 negative 5, we'll have 1, we'll have 0, and we'll have negative 7. Now, why do we have a 0 in there? Because if you look at your original function, you need to represent every single term's coefficient, including the missing terms. So that means that I have 2 for that x to the 4th power term. I have negative 5 for the x to the 3rd power term. I have 1 for the x squared term, and I have 0 for the x to the 1st power term. And then, of course, my constant, negative 7, aka that x to the 0 power term there. Okay, so we want to go in line as saying, as far as the degrees are concerned, 4, 3, 2, 1, 0. As far as the degree on each term is considered. So, that being the case, let's go ahead and continue our synthetic division process. You'll be bringing down that first coefficient of 2, then multiplying by the divisor 4. We'll have 4 times 2 gives you 8. We'll then combine that to get a 3. 4 times 3 is going to give us 12. Then we'll add that to get 14. All right. Excuse me, 13 rather. And then 4 times the 13 gives us 52. Bringing down that 52 here. Then we'll have 4 times 52, which is going to be 208. And then combining negative 7 and 208, guys, you're going to end up with 201. Now, doesn't this value of 201 look familiar, guys? This is the remainder of our synthetic division, and it is identical to the value of 201 that we found here after doing 1,000 steps. That's the benefit of knowing the remainder theorem. There you go. Just right there. That instead of going through this entire process of simplifying this by plugging in the value of 4, by doing the order of operations and simplifying that, instead of doing that, we can use the remainder theorem and this short process here of synthetic division to get the exact same result. And it works every time. With problem number 2, it says that if f of x equals x cubed plus 3x squared plus 2x plus 8, we want to evaluate f of negative 3. We want to evaluate f of negative 3. And what are we going to do with this information? We're going to use the remainder theorem to evaluate the original function by, instead of plugging in negative 3 for the value, oh no, we'll be using that synthetic division and the remainder of that to end up with the correct result. Let's see how that looks. We'll be setting it up as with the negative 3 on the outside here, having our synthetic division set up, and we have 1, 3, 2, and 8 as our values, those coefficients that we'll be using in order to simplify this problem, in order to find out what the value of f of negative 3 is using the remainder theorem. So start out by bringing down this 1 here. We'll then have negative 3 times 1, which gives you negative 3. This gives you 0. Then negative 3 times 0 gives you 0. We'll bring down that 2 after combining those terms there. And then we have negative 3 times 2, which gives you negative 6. And then combining 8 and negative 6, you'll end up with a value of 2. Yeah, you'll end up with a value of 2. Just like that, guys. Just like that. And so therefore, the remainder is going to be our value of f of negative 3. So instead of plugging in negative 3 into the original function and simplifying it, we were able to find out the value of f of negative 3 by using the remainder theorem. Done and done. Yeah, done and done, guys. So this is the result of f of negative 3 into our function f of x equals x cubed plus 3x squared plus 2x plus 8. Done and done. And this is problem number 2. Continuing on. All right, here we have it. Our next problem, guys. Example 3, we're asked to evaluate the function at the given value. So in a problem like this, where we have f of a equals a to the 4th power plus 3a cubed minus 17a squared plus 2a minus 7, it's going to tell us that they want us to give the value at a equals 3. So instead of plugging in 3 into the function and simplifying it, we'll be using the remainder theorem to find out what that value is. All right, so it looks like this. We'll go ahead and set up our synthetic division. We'll need all of the coefficients from the function in descending order of the variable a. So we have 1, 3, negative 17, 2, and negative 7. So according to the degrees of the terms here, we have 4, 3, 2, 1, and 0, taking all of those coefficients. Once we have that, we'll be bringing down that first value, which is 1, and then 3 times 1 gives you 3. 3 plus 3 is 6. 3 times 6 gives you 18, and then combining negative 17 and 18, you end up with 1. 3 times 1 gives you 3. And then when you combine the 2 and the 3 together, you get 5, and then 3 times 5 gives you 15. So now, finally, in order to get this remainder, you're going to combine negative 7 and 15, and that gives you a value of 8, which is the answer to this problem. That's right, we'll be red boxing it. Problem number 3, done and done. So we just evaluated the function at the given value, and so when they have it set up like this, you'll simply plug in this value of a directly into the synthetic division and go from there. So that's problem number 3. We have it in a red box, and we're going to continue on with the next problem. Here we go, guys. Problem number 4. With problem number 4, we have the exact same directions. Yeah, we do. It says to evaluate the function at the given value, and our function in this problem is f of x equals x to the 5th power minus 47x cubed minus 16x squared plus 8x plus 52 at x equals 7. Now that we have this problem, we're going to use the remainder theorem to solve it. That's exactly what we'll do. So once again, when they have it in this setup, in this form right here, you go ahead and you use your 7, all right, as a divisor into your synthetic division, okay? And we'll need all of the coefficients in descending order of your variable when you're setting it up, okay? So that means I'll need a 1 for that x to the 5th power term. I'll need a 0 for the x to the 4th power term. I'll need negative 47 for the x to the 3rd power term, negative 16 for the x squared term, an 8 for the x to the 1st power term, and then finally a 52 for our x to the 0 power term, aka the constant. And you'll be bringing down that 1. Go ahead and bring it down. Bring down the 1. Thank you. And then 7 times 1 gives you 7. 0 plus 7 is 7, right? Then we have 7 times 7, which is 49. Combining these values here, negative 47 and 49 gives us 2. From here, we'll multiply to give us 7 times 2, which is going to be 14. Combining negative 16 and 14 gives you negative 2. Multiplying 7 times negative 2 gives you negative 14. Yes, it does. Then we have 8 and negative 14 to give you negative 6. And multiplying 7 times negative 6 gives you negative 42. So when you combine these last values here, that's going to give you your remainder, aka the value of the function at x equals 7, which means that we'll end up with a result of 10. 52 and negative 42, when you combine those values, you end up with positive 10, which is the answer in a red box. And that's what we have for problem number 4. That is what we have for problem number 4, ladies and gentlemen. All right, that's problem number 4. What do you think? Not too bad, right? Not too bad at all. Okay, so here we have problem number 5. And in problem number 5, it says to use the remainder theorem to determine if the given number c is a 0 of the polynomial. Now, when they're referring to zeros when you're dealing with polynomial functions, they're referring actually to the x-intercepts. So they're asking you, where on the x-axis does this function touch the x-axis? So what we want to do is we want to use the remainder theorem, and if that last value, if that remainder equals a 0, then that guarantees that this value c is a 0. You want that last number to equal to 0 in order to verify that you have a 0 of the polynomial function. We have the following. We have our 2, and we'll be placing this 2 on the outside of our synthetic division here. We'll use our coefficients of 1, 3, negative 7, 13, and negative 10 here. And then we'll be plugging these values into our synthetic division, making sure that you have each and every term represented, their coefficient in descending order of the variable x. So how do we verify that? Just look back at your function here, and all those coefficients starting from the x to the fourth power term all the way down to the x to the 0 power term, you want to have those represented in your synthetic division setup. So the coefficient on the first term is 1, coefficient on the second term is 3, the coefficient on the third term is -7, and so forth and so on. We have a positive 13 and a -10. So bring down that first value of 1, then multiply 2 times 1 to give you 2. Adding 3 plus 2 gives you 5. 2 times 5 gives you 10. We end up combining the -7 and 10 to give you 3. 2 times 3 is 6. 6 and the 13, the 6 and the 13, they'll add to give you 19. 2 times 19 is going to give you 38. And then combining -10 and 38, we end up with 28 as our result. And because 28 is the result, guys, hold on here. Remember, we were supposed to be determining if the given value c is a 0 of the function. Well, it's not. How do we know that? Because this last value is not 0. So the answer to this is no. C equals a 2 is not a 0 of the polynomial. And we know this because our last value here is not 0. That's how we know that. And that's why we'll be putting a red box around this. That's right, Chosen Creeper. Chosen Creeper says this is understandable. Okay, so here in problem number 5, we have part B. Notice that previous problem was part A. So for part B, guys, it says use the remainder theorem to determine if the given number c is a 0 of the polynomial. This time we have the exact same function here. We have the same function f, but this time, Chosen Creeper in Ghost World, we have c equals to -5. So that's c what's happening. Let's see what happens here when we plug in -5 into our synthetic division to see whether or not, to determine, to verify whether or not -5 is a 0 of the polynomial. That's what we want to check out. So with this, we have our coefficients from the original function. It'll be 1, 3, -7, 13, and -10. And once we have this set up, we'll be, of course, bringing down this value of 2, the value 1, bring down that first value, and then multiplying -5 times 1 to give us -5. Then combining 3 and -5, you get -2. Multiplying -5 and -2, you end up with positive 10. -7 and 10 combine to give you 3. Multiplying -5 times 3, you get -15. Adding 13 and -15, you get -2, and then multiplying -5 times -2, you end up with positive 10. And once you combine that, notice that we end up with a remainder. Our remainder here is 0. Anytime you end up with a remainder of 0, that confirms that you are dealing with a 0, aka an x-intercept of the original function. So the answer to this is yes. Yes. -5 is a 0 of the polynomial. So we can use the remainder theorem to verify whenever you have x-intercepts. So whenever you're dealing with x-intercepts and you need to verify that, you can use the remainder theorem, okay? So this can be utilized in many, many different ways, so that it is so important, so you can have this in your tool belt, so that when you have certain questions in your math classes, you can answer them. That's right. With confidence. All right, and efficiency even, because we could have, of course, used the function notation and plugged in -5 into the original function, but in many cases, that may take you a lot longer than just simply using your synthetic division here and checking out the remainder to see whether or not it equals to 0 or not. All right, a lot of times this process can be a lot faster than you plugging in the value into the original function and then simplifying it. All right, so that's problem number 5 with a red box around it. That's right. That's how we do our answers here at Fort Bend Tutoring. We put our answers in a red box. That's exactly what we do. All right, so here we go, guys. We are going to continue on with the fact that I want to remind you that here at Fort Bend Tutoring, you can always set up a paid online tutorial today at FBT Fort Bend Tutoring. Just go ahead and check out our website, which is going to be tutormemath.net. tutormemath.net, and you can set up a paid online tutorial with us to assist you in your math endeavors. That's right. So we do tutorials from middle school mathematics classes all the way up through university courses, college courses. That's right. That's right. So check out our offerings. In addition to that, we also do test proctoring. So if you are out there and you ever need test proctoring, especially if you're in the Houston, Texas area, Missouri City area, the Sugarland area, Fresno area, Stafford area, we can assist you with any test proctoring that you may need. Amen, amen. All right, so go ahead and check out our website, and let's get back to the remainder theorem. Here we have problem number 6, and in problem number 6, we're asked to verify that the given value is a 0 of the polynomial function. Remember, if you need to verify whether or not a value is a 0 of a polynomial function, use the remainder theorem, and you want to make sure that that last value is 0. That's right, that the remainder equals 0. If the remainder equals 0 in your synthetic division process, then you can verify that the polynomial function is a 0. All right, so let's check it out. We'll end up with our setup with 2 on the outside here. We'll have our coefficients 1, -1, -1, and -2 here. That's what we got. And we'll be bringing down this first value, which is 1, and we will multiply. We have 2 times 1, which gives us 2. -1 and 2 combine to give you +1. 2 times 1 gives you 2. Combining -1 and 2, we end up with 1. Then multiplying 2 times 1, you end up with 2. And lo and behold, you'll end up with a result of 0. Once again, this confirms that you are dealing with a 0 of the polynomial function. Yes, it does, because the remainder is 0. That's right. So if that remainder is 0, then that means that the answer to this problem is a yes. Yes, this is a 0 that we're dealing with. Why? Because the remainder is 0. That's how we can confirm that. All right. So there you have it. Problem number 6A, guys. That was problem number 6A, and we're moving on. Moving on to part B. And in part B, we want to verify that the given value is a 0 of the polynomial function. That's what we want to do here. That is exactly what we want to do. So we have the same function f. Yeah, we got the same function f here. That f of x equals to x cubed minus x squared minus x minus 2. And this time, we'll be seeing if -1 is a 0 of our polynomial function using the remainder theorem alongside synthetic division. That's right. So we're going to be placing that -1 right here, setting up my synthetic division with 1, -1, -1, and -2. Okay. I don't know about that negative sign right there. Let's go ahead and fix that. There we go. There we go. A lot bolder negative. And bringing down the first value of 1, we'll multiply. We have -1 times 1 to give us -1. Combining those values, you'll end up with -2. Multiplying -1 and -2 gives you +2. That gives you a value of 1. Then multiplying -1 times 1, you end up with -1. And your result here is -3, not 0. You want this value to be equal to 0, ladies and gentlemen. And it is not. It's not. No, that's a -3. I mean, I'm looking at it right here. There you go. So there you go with -3. And that means that this is not. No, it is not a 0. All right. So Lewis says, sometimes my screen freezes, but your voice is heard live only. I understand, Lewis. Unfortunately, I'm putting out a bad signal right now. We have problem number 7. We're going to be verifying that the given value is a 0 of the polynomial function. If you can only hear me now, that's right. I apologize for the stream. But we have f of x equals x cubed minus 3x squared plus 4x minus 12. Once again, that function is x cubed minus 3x squared plus 4x minus 12. And this time, we'll be testing to see whether or not the imaginary complex value -2i is a zero of the polynomial function. All right, so this will be the first time that we're doing a problem like this where we're dealing with an imaginary value this time. So let's go ahead and set up this synthetic division for the problem. We'll have negative 2i on the outside of my synthetic division setup, and we have 1, negative 3, we have 4, and negative 12. Chosen Creeper says, I'm testing some problems in an online graphing calculator to see if it really works. Good job there, Chosen Creeper. I appreciate you testing that out to see if that works out just fine. And you should see, if you graph that all of the zeros that are verified will be x-intercepts. Good stuff. And once again, guys, I want to apologize for this bad stream. It is out of my hands with the internet connection. But once again, when everything is said and done today, I will be later on today re-uploading this video so that you can see it in its entirety and get better use out of it. All right, what's going on, Obina? Good to see you, Obina. Sorry that the stream is wonky today. All right, so thanks for stopping by, Obina. Good to see you. So let's start here, guys, by bringing down our first value of 1. Remember, we're using an imaginary number as our C value this time. And negative 2i and 1 multiply to give you negative 2i. Just like that. So what you'll do is you'll be bringing down the value negative 3 minus 2i when you combine this, okay? So this is negative 3 minus 2i, as these are unlike terms at this point. Then you want to multiply, aka distribute, the negative 2i with this negative 3 minus 2i. So let's see what that looks like, okay? So if we were to multiply this negative 2i times negative 3 minus 2i and then distribute that, you'll have negative 2i times negative 3, which gives you 6i, and then negative 2i times negative 2i is going to give you positive 4i squared. However, remember that I squared is equivalent to negative 1. So you'll rewrite this as 6i plus 4 times negative 1 and end up with a result for this particular product, which is going to be negative 4 plus 6i. Okay, you'll have negative 4 plus 6i. So that's what I'm going to be bringing down here as our product from multiplying negative 2i and negative 3 minus 2i. So we're multiplying the imaginary numbers here, the complex numbers, to get a product of negative 4 plus 6i. Now when we combine these terms together, the 4 and the negative 4 plus 6i, the 4's will cancel out, right? So I'll be bringing down 6i as a result. I'll be bringing down 6i as a result. Then, guys, I'll be multiplying negative 2i and 6i. Well, let's see what happens with that, right? So let's go ahead and get this out of the way real quick is what I was trying to say. We'll then multiply the negative 2i times 6i, and then multiplying negative 2 times 6, you'll end up with negative 12i squared, right? Well, once again, I squared, that value is equivalent to negative 1. So when you multiply negative 12 times negative 1, you end up with positive 12 as a result. And lo and behold, guys, this confirms that negative 2i is actually a zero of our original polynomial function. Yeah, and we know that because the remainder is 0. We see that the remainder is 0, which confirms that we have negative 2i as a 0 of our original polynomial function. So the answer to this is yeah, it's yes. Yes, negative 2i is a 0 of the polynomial function because using the remainder theorem, our remainder equals to 0. And that only occurs when we have a 0 of the original polynomial function. Done and done. Obina says yes, the given value is a 0. Good job, Obina. Good job. And we know that. Why? Because the remainder is 0. And that is using the remainder theorem to its fullest. Good deal, guys. All right. Let's continue on. We're looking at part B. We have verified that the given value is a 0 of the polynomial function. Once again, this polynomial function f is identical to part A, which is f of x equals x cubed minus 3x squared plus 4x minus 12. This time, we'll be seeing if 3, the value 3, is a 0 of the original polynomial function. So once again, using synthetic division, using our C value being 3, we'll have coefficients 1, negative 3, 4, and negative 12 from our polynomial function. Plugging these values in, continuing the synthetic division process, we'll be bringing down 1 here. We'll have 3 times 1, that gives us 3. Negative 3 and 3 combine to give you 0. 3 times 0 is 0. 4 plus 0 is 4. Thank you very much. And, of course, we'll have 3 times 4, which gives us positive 12, and negative 12 and 12 give you 0. Turns out that 3 is also a 0 of our polynomial function. So once again, this answer is yes. Yes, 3 is a 0 of the polynomial function because the remainder is 0. All right. I understand, Chosen Creeper. You got to go. It's 2 a.m. here. Take care, and thanks for spending some time with us today, even though the stream is a hot mess. The stream is a hot mess today, so I apologize for that, guys. So here we are going to continue on here. Let's go ahead and give Chosen Creeper a little love. All right. There he is. Chosen Creeper saying bye to us. All right. Take care, Chosen Creeper. All right, so I'll reload all of this back up to the channel today, guys, so that you guys can see it in its entirety. We'll be red boxing our answer here, guys. Red boxing it, just like that. Just like that. So we have problem number 7, part B. 3 is a 0. Because we ended up with a remainder of 0 after we plugged it into our synthetic division. And we'll be moving on to our next problem. That was problem 7b, guys. And now we have problem 8a. So we have our function f of x equals to 2x to the 4th power minus x cubed minus 9x squared plus 3x plus 9. We're going to be trying to see if negative 1 is a 0 of the polynomial function using the remainder theorem. Let's see what happens when we plug in negative 1. All right, so we'll be using our coefficients 2, negative 1, negative 9, 3, and 9. We'll be bringing down the 2 here. Negative 1 times 2 gives you negative 2. All right, from here, this is going to give us negative 3. Then multiplying negative 1 and negative 3, you get positive 3. We'll be bringing down a negative 6 here. Negative 1 times negative 6 is positive 6. Adding 3 plus 6, you get 9. And negative 1 times 9 is negative 9. So that gives you 0. Obina says Mr. Witt's internet connection is bad. That's right. Yeah. It's my bad, Angry Hermit. Sorry about that. I'll be re-uploading the video later on. No, Nathan, it is on my side, not your side. Yeah, the internet connection on my end is terrible, okay, for today for some reason. And so what we'll be doing is I'll re-upload the video later on today. All right. Thanks for your patience. I really do appreciate that. All right. So, guys, notice that our remainder here is 0, as it should be. So the answer to this is yes. All right. The answer to this is yes, that this is, oh, my goodness, that this is a 0. Negative 1 is a 0 of the original function. So this is what we have. Done and done for part A. All right, so let's move along, guys. Let us move along. We have part B. And part B, once again, we have a fraction. We hadn't tackled fractions before as far as our values of C are concerned. But today, oh yes, right now, we will. So we'll be utilizing the same function. We have a C value that's 3/2. And so that being the case, you have 3/2 going into, that's right, Lewis, is called doing it live. And doing it live has its disadvantages, such as what happens when your internet connection is starting to trip out. Well, you keep going. That's what you do. And hopefully you have a backup recording so that you can upload that recording, and so everything will work out. So that's what you do when you're live streaming and things go awry. Make sure that your computer is set to record everything that you're doing regardless of the stream. So we'll be bringing down the number 2. Then multiplying 3/2 times 2. We're going to have the 3/2 times the 2 here. The 2's will cancel out. You end up with 3. Thank you for understanding, Angry Hermit. And we'll have a 3 right here. The negative 1 and 3 is going to be combining, and we'll end up with a positive 2 now. When you multiply 3 halves times 2, and let me go ahead and show that step, guys. Multiplying that 3 halves times the 2, which is over 1 here. See, you can have your 2's simplify, then multiply to get 3 over 1, which reduces to give you 3. And that's going to be what happens when we do this. So we end up with a 3 right here because of that product. Then combining the negative 9 as well as the 3, you end up with negative 6. Then multiplying 3 halves times negative 6. Let's go ahead and show what that looks like. All right. So we know that you guys love yourselves some fractions, right? I know you do. I know you do. I know you love the fractions. See, 2 goes into itself once. 2 goes into negative 6, negative 3 times. Then multiplying straight across, you'll end up with negative 9 over 1, which is negative 9. So we'll place a negative 9 right here and then combine that. So 3 and negative 9 give you negative 6. And what happens next? You'll be multiplying 3 halves times negative 6 again. And what do we get? We get a negative 9. And once you get that negative 9, this will end up resulting in a 0 for your result. So because our remainder here is 0, then once again, what's going on, AN? How's it going there? We are dealing with a bad internet stream on my end today. So just to let you know, that's what the deal is, Ann. But thank you for stopping by. I appreciate it. And so here we have 3 halves as the C value, and we end up with 0 as a result. All right, so our remainder here is 0. So this confirms that 3 halves is a 0, guys. So this answer here is a yes. Yes, yes, yes. That this is a 0 of the original polynomial function. All right, good stuff, guys. All right, so Lewis is not on their end. It's on my end for certain. All right, because even my streaming software is telling me that my signal that's going out is terrible. All right, so I apologize for that. We have part C, guys. So in part C, we'll be testing to see if 1 is going to be a 0 of the polynomial function. Let's check that out. So setting this up, using our synthetic division, we have 2, negative 1, negative 9, 3, and 9 here. We'll be bringing down the first value, which is 2. We know that 1 times 2 is going to give you 2. Negative 1 plus 2 is 1. 1 times 1 gives you 1. Negative 9 and 1 gives you negative 8. 1 times negative 8 is negative 8. And then combining 3 and negative 8, you end up with negative 5. All right. So then multiplying 1 times negative 5, you get negative 5. And the result here is 4, not 0. Remember, we need that remainder to equal to 0 in order to confirm that your C value, in this case, the number 1, is a 0 of the polynomial function. That's right. So therefore, we got a no for part C. That's right. We have an N to the O in a red box. That's right. That's right. So Ann is saying, what's up to Angry Hermit? Everybody chiming in with Angry Hermit today. That's right. Showing some love to Ann, saying what's up there. All right. Good stuff. Nathan is asking, do I have a live stream schedule? Yes and no, Nathan. All right. Yes and no. But currently it is in Central Standard Time. It is every Friday at 12 p.m. is the current live stream schedule. All right, so part D, guys, I'm really excited about it because we have a C value that's an irrational number. It's in the form of the square root of 3. Square root of 3. And we're going to see if the square root of 3 is a 0 of this polynomial function. So recall that when we set this up, we'll be using synthetic division here. All right. And with our synthetic division, we'll have 2, negative 1, negative 9, 3, and 9 as our coefficients that we're using in our synthetic division process here. We'll be bringing down the value 2, and then multiplying the square root of 3 times 2, you end up with 2 times the square root of 3. Because these are unlike terms, you can bring it down as, I think I'm going to bring it down as 2 square root of 3 minus 1. All right. So you could bring it down as negative 1 plus 2 times square root of 3. It's up to you. It doesn't matter. But now we'll need to distribute this. So let's see what happens when we distribute the square root of 3 times this 2 square root of 3 minus 1. Okay. Well, distributing that, the square root of 3 times 2 times square root of 3 will give you 2 times 3. Then square root of 3 times negative 1 is going to give you a negative square root of 3. From here, you can multiply the 2 times 3, which gives you 6 minus the square root of 3. So that's what I'll have here. I'll have 6 minus square root of 3. And then we'll be combining negative 9 with that 6 minus square root of 3. So this gives us a result of negative 3. It gives us negative 3 minus the square root of 3. Okay? And we'll need to multiply the square root of 3 times this negative 3 minus square root of 3. So what occurs is we'll multiply this the square root of 3 times the negative 3 minus square root of 3. We'll distribute, of course, we get our arrows popping here. Thank you very much. So we'll have the square root of 3 times negative 3 gives you negative 3 times the square root of 3. Then square root of 3 times negative square root of 3 is actually negative 3. Okay? We end up with this value because the square root of 3 times square root of 3 is the square root of 9, but the square root of 9 is 3. And because we're multiplying a positive times a negative, you just end up with negative 3 here. So that's what I'll be bringing to the table here. We'll have negative 3, the quantity, negative 3 times square root of 3 minus 3 right here. Okay, and then what happens is those 3's will cancel out. You'll bring down, let's move things over here, guys, because it's all jumbled up over here. Okay, let's see if we can give ourselves some room. There we go. We have a result here that's going to be negative 3 square root of 3. Okay, so that's what we have after we combine the 3 with the negative 3 square root of 3 and the negative 3. All right. Now, okay. Oh, yeah. So Angry Hermit says, I chose to work as a means of becoming more disciplined. Thank you, because everybody can use a little dash of discipline in their lives, including me, Angry Hermit. So you're absolutely right. So speaking of being disciplined, let me be disciplined to complete this problem. So we want to now multiply, guys, our square root of 3 times the negative 3 square root of 3 here. So what happens when you multiply the square root of 3 times the negative 3 times the square root of 3? Well, let's see. We know that we'll have a coefficient of negative 3. We know that, right? Because 1 times negative 3 is negative 3. But when we multiply the square root of 3 times square root of 3, we'll end up with 3. Nathan is asking, Angry Hermit, is that going to be is that part-time work or is that full-time work? So we end up with negative 9 as a result of that product. So now we'll have negative 9. We'll be adding that to the 9 that we have there, and 9 minus 9 is going to be 0. So what does that mean for us, guys? That means that we have just confirmed that the square root of 3 is a 0 of our polynomial function. This answer is yes, Obina. The answer is yes. We end up with a remainder of 0. So this verifies that we have a 0 in the C value of negative 3. Yeah. In other words, the C value square root of 3. Square root of 3 is what I meant to say. That square root of 3 is a 0 of the polynomial function. There it is. Square root of 3 is a 0 of the polynomial function. We know this because the remainder is 0. There we go. Yeah. So yeah, so it's a little ugly here, but you know, we're gonna make do with this. Yeah, we're gonna make do with this. This was the result of problem number 8, and now a new problem. Yeah, problem number 9. Problem number 9. So it says to state if the given binomial, not polynomial, polynomial, Bollywood. So anyway, state if the given binomial, thank you, is a factor of the given polynomial. So how do we do that, guys? We need to first of all recognize that what they've given us, the divisor here, the divisor is in the form of x minus c. So the first thing to do is to find out what your c value is by placing this factor, placing the divisor, setting it equal to 0, and then solving for it. So if we solve for this, we'll end up with p equaling 2, aka our c value would be 2 in this case. All right. So because of that, we'll be going ahead and using 2 as our divisor in the synthetic division process. All right. There you go. So with that said, we'll need our coefficients from our dividend, which is going to be 1, negative 8. Oh, that's ugly, negative 8. Let's fix that. There we go. That's better. Negative 8 there. We have 10. We also have 2. And we have 4. Okay. So bringing down our first value, bringing down this first value of 1. We have 2 times 1, which is 2. The negative 8 and 2 combine to give you negative 6. 2 times negative 6 is negative 12. We'll combine those values to give us negative 2. We now have 2 times negative 2 that gives us negative 4. Bring down the negative 2, and 2 times negative 2 is negative 4, and this gives you a remainder of 0, which means that this binomial is a factor of the given polynomial. Since it terminates, that verifies that this binomial here will divide evenly into the original function. So this is an alternative to verifying whether a divisor will go into a given polynomial. Instead of using long division, you could use the remainder theorem to assist you in that process. All right, so that is why this answer here is yes. Oh yeah, we have a yes here. Notice the red box around the answer yes. There you go. So this is our result, ladies and gentlemen. This is what we got. This is what we have. This is problem number 9. Yeah, problem number 9, just right there. There it is. Remainder theorem in the house. In the house, and continuing on with problem number 10. In problem number 10, guys, and gals, it says to state if the given binomial is a factor of the given polynomial. Angry Hermit says, okay, my screen is frozen, so I guess I'm going to go too. Thanks for the stream, Mr. Witt, and I'll see you all later. I understand, Angry Hermit. No problem. Take care. Take care. Like I said, it's not your fault. It's mine. And hopefully the internet connection will be better next week. Take care, guys. All right, so here on our last problem, we are stating if the given binomial is a factor of the given polynomial. And what we want to do is we want to, first of all, find out what our C value is. And how do we go about doing that, guys? Well, you'll take the divisor, set it equal to 0, and solve for n. So we'll have n plus 5 equal to 0. Solve for n by subtracting 5 to both sides of the equal sign here. You'll have n equals negative 5. Then from there, you're going to go ahead and place this into your synthetic division. We'll have negative 5 on the exterior. Within this, we'll have all of the coefficients of the dividend. So that means that we'll have 1, 0, because we don't have an n to the 4th power term. Then we have negative 25. We also have negative 7. We have negative 37, and we have negative 18. All right, and we have a lot of room that is needed for this problem. So we're going to need to move this over here and get things in order. There you go. So we had negative 37. We also need negative 18. So there we go. Let's go ahead and extend that. All right, so we'll have more room. Lewis says he likes that polynomial. Thanks, Lewis. Appreciate it. I thought it was clever. So here we're going to be bringing down the 1. We have negative 5 times 1. That gives us negative 5. 0 and negative 5 is negative 5. Multiplying negative 5 times negative 5 is a positive 25. So that gives us a value of 0. Negative 5 times 0 is 0. We'll be bringing down we'll be bringing down negative 7. All right, let me not rush. Negative 7 plus 0 is negative 7. Thank you. Then multiplying negative 5 times negative 7 gives you positive 35 here. Combining negative 37 and 35 gives you a result of negative 2. Then multiplying negative 5 and negative 2, you get positive 10. All right, well, this result here, guys, is negative 8. So that means that this answer is no. We needed that last value, the remainder of the synthetic division. We needed that to equal to 0 to verify that the binomial was actually a factor of the given polynomial. In this case, it is not. So this is no. It's not happening. This binomial is not a factor of our given polynomial. And, ladies and gentlemen, we are done with today's lesson. We had the remainder theorem. Once again, guys, I am apologizing for the terrible stream. I will be re-uploading this stream in its entirety either later on today or by no later than tomorrow. You'll see the actual video for this because today's stream sucked for some reason because of the internet connection. But please give us another shot, and Obina was correct about that. Nope, the binomial isn't a factor. And please go ahead and remember to subscribe to FBT Tutoring FBT. This is Mr. Witt, and this was the Remainder Theorem. Please rate, comment, and subscribe. Peace.
Thanks for watching. We appreciate you hanging out with FBT Tutoring. Like the video, comment, and subscribe. Hit up our website, tutoringmath.net, and set up a private tutorial with me and FBT. Oh yeah, baby. Thanks for watching. We appreciate you hanging out.